So this lesson is going to go over series and parallel circuits and some simple calculations to figure out some properties of those circuits. So we're going to first start with this simple circuit diagram here, and we're just going to go over some things. Wait a second, that's the wrong picture. Just kidding. So the first thing, we're going to start real simple. What do these three symbols mean? The one on the left is a current source, the one in the middle is a voltage source, and the one on the right is a resistor. So the resistor, we've been dealing with some light bulbs in class, but the resistor you can just think of as a light bulb or some sort of other load. A really good example of a resistor is a ceramic heater. It just has a resistor in there that gets hot. And a voltage source is just a battery. Okay, so first we want to cover two simple circuit laws. So one is Ohm's law, that the voltage equals the current times the resistance, or V equals I times R. Voltage is volts, or V is voltage in volts, I is current in amps, and R is resistance in ohms. And the symbol for that is the Greek letter omega, pictured here. So second, we wanted to go over the power law. So the power law is that the current times the voltage equals the power in watts. So the way I like to think about this is why this is power is that you can think of current as sort of water flow and voltage as pressure. So if you actually think of a super soaker, the size of the nozzle is the amount of current that flows out of the gun, and the amount of times you pump it is the voltage. So a really powerful super soaker is going to have, you're going to pump it a lot of times, but it's also going to have a big nozzle. So that's why you multiply them together. And if you have no pumps or no flow, you have no power. So that's the way you can think about it. Okay, so let's start with this simple circuit example. So the first question I want to ask is, what's the voltage drop across the resistor in the following circuit? And what's the power delivered? So the current, basically we know, is 3 amps. And the current is always the same when you're looking in a simple circuit like this. There's no branches for the current to branch off, so it's always the same. So if we look at the voltage, it equals the current times the resistance, so that's 15 volts. And then the power is the current times the voltage. So that's the 15 volts times the 3 amps. So really simple circuit. So let's move on. So now it's the same simple circuit except we have a voltage source. So we do the same thing. In this simple one, the voltage is the same over here. So V divided by R, 12 volts over 5 ohms, so 2.4 amps. And then the power is 2.4 amps times 12 volts, so 28.8 watts. Okay, so before we get into more complex circuits, we really have to think about which way current flows. So it turns out that current is a little counterintuitive, as you can see from this Benjamin Franklin comic. So the direction of current flow is the direction a positive charge would flow. Why is this counterintuitive? Because the negatively charged electron is actually moving. So our direction of current flow is actually backwards for the way electrons are actually flowing in the circuit. But that was the way it was defined, and that's why in this comic the electrical engineer is going back in time to alert Benjamin Franklin. So the other thing we want to know is that when current flows into a resistor, it's the positive side of the resistor. So I'll show you what I mean in some examples, but basically whatever side of the resistor the current's flowing into is the positive side of the resistor. So let's look at this example. The first thing we want to know is what this notation means is the small part of this voltage source of this battery is the negative side, and the longer side is the positive side. So the first thing we want to know is which way would the current flow? Well, the way I like to think about it is that if I put a positive charge, you remember that like charges repel. So if I put a positive charge here, it's going to go this way because it's going to repel away from the plus. And if I put a positive charge this way, or if I put a positive charge here, it's going to flow this way because it's going to attract to the minus. So that's the way our current flows in this circuit, and current always flows in a complete loop. So which would be the positive side of the resistor? So you just have to remember that whichever way the current flows into the resistor is the positive side. So this is the positive side of the resistor. So now we're going to get into two laws of circuits. And the first is Kirchhoff's current law. And all that means is that the sum of currents at any node, and all that means is where wires go into a branch, is equal to 0. And all that really means is that the current that's going into the node has to go out of the node. And think about it in terms of pipes. If you had two pipes going into a valve and one pipe coming out, all the water that's going into the valve has to come out. So it's the same thing with electric current. In other words, all flow has to be accounted for. Then we have Kirchhoff's voltage law. And Kirchhoff's voltage law that just says that in a circuit, the voltages in any loop must add up to 0. And basically, this is just same thing as pressure in a loop of a hose or pipe. So the pressure must be 0 in a loop. Okay, so let's take a look at this example circuit. So what we want to do here is the first thing we want to do is label all currents in the circuit. So that's why I have I1, I2, and I3. Then we want to see the direction they flow. So we know they flow out of the positive side of the battery. And then they split off here. So this, since this current's flowing into this node, we know that these two are going to flow out. Now we want to apply KCL at the nodes. So basically all it means is that the sum of currents going into the node, so this I1's going in, equals the sum of currents going out of the node. So I2 plus I3. Okay, and I3 looks like it might not be coming out of there, but really it's, if you follow the same wire around, I3 is right there as well. So let's look at, then what we want to do is have an example of Kirchhoff's voltage law. So we're going to find all the loops in the circuit, which in this case there's 2 loops, and then we're going to put positive and negative signs on the resistors depending on the way the current is flowing. So let's go ahead and do that, and we know it's the same as our last things because we already labeled the current flow. Now we're going to apply Kirchhoff's voltage law at all the loops. If a loop goes into a positive end of the resistor, the voltage is positive. If the loop goes into a negative end, the voltage is negative. So let's look at this one. Remember, the sum of voltages in a loop equals 0. That's what Kirchhoff's voltage law says. So let's look at loop 2 first. So we know that the voltage across R2, it's going into the positive, the loop's going into the positive end, so that's a positive. And then this one's going into a negative, so that's a negative. So the VR2 plus negative VR1 equals 0, which rearrange it with a little algebra, and we get that the voltages are equal. We can do the same thing with loop 1, and we find that basically these two voltages are equal as well. So the other thing to know is that the if we rearrange the loop 1 and loop 2 equations, that all the voltages are equal. And this is called a parallel circuit, and that's one of the properties of parallel circuits, that all the voltages are the same. But really, it's not that it's a parallel circuit, it's because it's a consequence of Kirchhoff's voltage law being applied to the parallel circuit. Okay, so now we're going to analyze the following circuits. The top is a parallel circuit, and the bottom is a series. So that you can see they both have the same voltage, and they both have the same 2 resistors. So let's start with the parallel. So fill in what we know. Well, we know that all the voltages in a parallel circuit are the same, so all the voltages are 12 volts. So again, we could have applied KVL, but I just showed you that before. Now we know the voltages across the resistors, and we know the resistance, so we use Ohm's law to find the current. So I equals V over R, and that's all we're doing here. Then we know that we could either use Kirchhoff's current law up here or up here. And we find that the current going in, the I from V1, equals IR1 plus IR2. And we knew that IR1 and IR2 equals this, so you add them together, you get the 4.1 amps. Now, there is another way to do this. So we can construct an equivalent circuit by combining the resistors into equivalent resistance, or R equivalent. Then we can use Ohm's law to get the current out of V1, and it gives the same solutions. So if resistors are in parallel, the equivalent resistance is equal to 1 divided by 1 over R1 plus 1 over R2. So if you plug in 5 and 7 for R1 and R2, you get this, the 2.917. And then we have our simple circuit, and so it looks like one of the simple examples I did before, and we use Ohm's law, and we get that the current running through it's 4.11 amps. So we get the same result for IV1 there of 4.11 amps. Okay, so now we just need the power law, that the power equals I times V, to get the total power of each circuit element. So the other thing to notice is that the power that the battery delivers is the same as the, if you add these two up, that the resistors are using. So the other thing to notice is that the voltage is all the same, but the current is different in a parallel circuit. All right, so now let's get the series one. In a series circuit, there are no branches for the current, so all currents are the same. The question is, how do we calculate it? So think about it like this. All the current flowing out of the battery is going into this resistor, is going into here. So all the currents are the same. So what we do is we actually just use KVL. We have one voltage loop, and we know basically it's going into the positive end of both of these resistors. So that's why VR3 and VR4 are positive. And it's going to the negative end of this battery, so that's why it's a negative 12. So, okay, that's great, but we don't know VR3 and VR4. So we write VR3 and VR4 using Ohm's law in terms of the circuit current, or I. So this VR3 equals I times R3, and VR4 equals I times R4. So then the nice part is that we don't know I, but we know R3 and R4, so we plug those in, and now we have one equation and one unknown. So we can go ahead and just solve for I, and I turns out to be 1 amp through the algebra. So there is another way to do this, because this is a bit cumbersome. So instead of using KVL, we can again employ equivalent resistors to get the total current. So for series, the equivalent resistance is actually much easier. It's just R3 plus R4. So that's 12 ohms. And then you can see that once we have 12 ohms, that V1 over REQ equals 1 amp. So it's the same solution. So if we just show that, now we have the current. Now we know the current's the same in all of our circuit. We can say that 1 amp, we use Ohm's law to get the voltage. And then we can multiply I times V to get the power. And again, the power used of both resistors equals the power delivered by the battery. So one thing to notice about series circuits is that the current is always the same, but the voltage is different. Okay, now let's get one more complicated example. So this is the circuit we're going to do. It's a little more complicated. So we could employ KVL and KCL, and it would be fine. We could definitely do that. However, the easier way to do a more complex circuit like this is to use our knowledge of equivalent resistors. So let's try that. So what we're going to do is we're first going to use the fact that that REQ, the equivalent resistance here, these are parallel resistors. So the equivalent resistance here is this equation, and it's 666.67. And then we have this circuit. These are in series, so we add those two together, and we get a little over 1100. Now we have a really simple circuit, and we can find the current. Okay, great. So we have the total current, but what do we do next? So we notice that the total current here is the same as the current coming out of the battery here and the same coming out of the battery here. So we're going to solve for the voltage across R1 and the voltage across REQ1. So how do we do that? Well, the current's the same here. So we know the current across both of these. So the voltage across R1 is this many volts, just the current times R1. Same here. So now the tricky part is doing the current on R2 and R3. Well, how do we know the VR2 and VR3 is this 0.285 volts? Well, the nice part is that the voltage across REQ1 is the same, since this REQ1 is a combination of these two in parallel, and we know voltage is the same in parallel, then the voltage across here is the voltage across these two. So that's why we can do these last two calculations. So then we fill in our table with what we know. So that's pretty much it for these calculations. These can be a little bit tricky, but as you're doing the problems, and as you're doing these type of problems, just really sit down, and you can always do KVL and KCL. So you just do KVL at every loop and KCL at every node, and you'll get the answer. But the easier way to do it is to use equivalent resistances. Thanks for watching.